This is a video to help you with your new gravitational fields assignment. So we're just going to go over 7 questions that are similar to the ones in the assignment. And hopefully you can figure everything out. The first question is find the gravitational field strength of a planet where a 75 kilogram person weighs 1,400 newtons. So we don't need to do this, but let's just for interest's sake, let's find out what the weight of the person on Earth would be. So on Earth, and this is just for comparison, you don't really need to do this in the question, but on Earth, the person's weight would be 75, be mg. Let's be thorough here. Mg. So the person's weight would be 75 times 9.81, which is 9.81 times 75 equals 0.75. So just as an interesting note, on Earth, that would be a weight. On this planet, they weigh 1,400, so almost double. So the gravitational field strength on this planet is going to be quite a bit significantly redundant. It's going to be quite a bit more than Earth. But we're going to do it basically the same way. We're going to start with Fg equals mg. And what are we asking for? Find the gravitational field strength. We are looking for little g. So all we do for this question is solve for g. Fg is the weight. Divide those two numbers, 1,400 divided by 75, and you get 18.7. 18.7 newtons per kilogram. So the gravitational field strength of this planet is almost double that of Earth, which makes sense because the weight was almost double. That's number 1. Number 2 says the magnitude of the gravitational field strength on Mars is 3.71 newtons per kilogram. If the mass of Mars were halved and the radius were increased by a factor of 3, the new gravitational field strength would be. So gravitational field strength, that's G. G equals 3.71 newtons per kilogram, or meters per second squared. They're the same unit. We're going to have the mass of Mars, so it's going to have half the mass. And we're going to increase the radius. So this is all based on this formula here. The gravitational field strength equals big G times m divided by r squared. Or, more importantly for this question, the gravitational field strength is directly proportional to the mass and inversely proportional to the radius squared. So if m gets smaller, then gravity is going to get smaller. If the radius gets bigger, then the gravity is going to get smaller because they're inversely related. So we should know right away when we're doing this question, the answer is going to be considerably less than 3.71, because all of a sudden the planet has half the mass and it's twice as big, or not twice as big, it's 3 times as big. So the gravitational field strength of this new planet is going to be quite low. Here's how we do it. We just plug these factors in. Half of the mass. So we assume that the mass, because the mass of Mars is not given to you in the question. You're not expected to know what the mass of Mars is. So you just say, for the sake of argument, that the mass of Mars is 1. Now, if we have the mass, the new mass of Mars will be a half. Okay, and it doesn't matter that it's we're not putting in units or anything like that. This is just a relationship question. Divided by the radius was increased by a factor of 3. So the radius is going to be 3 times bigger. And again, we don't need to know the radius of Mars. We're going to say the radius of Mars, the initial radius of Mars is 1. Now the new radius is 3. So this r becomes 3, and we have to remember to square it, and then we simplify this fraction. Write it down here so you can hear me, which equals 1 over 18. 1 over 18. So that is the factor by which the gravitational field strength has changed. In other words, it's 1/18 of the original. So then we just multiply that number by the original field strength. 3.71 times, or just divide by 18. Oh, it's going to be small. And we get 0.206 newtons per kilogram. So the new field strength of this planet is very low, 0.206. That is, what is that? That's about 1/9 the gravitational field strength of Mars. If you were on this planet and you jumped, boy, would you go high. And very slowly, you'd feel like you're in slow motion. Okay, question number 3. Two objects exert a gravitational force of 10.5 newtons on each other. If the distance between them decreases to 3/8 of the original distance, what is the new gravitational force between them? This is very similar to the previous question, except for now we're dealing with this formula, the gravitational force between two objects. And yet again, it's more important that you know this, that the gravitational force is directly proportional to the product of the masses and inversely proportional to the radius squared. And on this one, all we're doing is decreasing the distance to 3/8 of the original. So if the initial distance between them, radius was 1, the new radius between them is 3/8. And we're going to do it exactly the same way we did the previous question. We're just going to say that Fg is inversely proportional to 1 over r squared. In this question, the masses of the objects are not changing, which equals 1 over 3/8 squared. And before we do any of this, we should have asked ourselves, is the answer going to be bigger or smaller than 10.5 newtons? So we take two objects. They have a gravitational force of 10.5 newtons, and then we move them closer. Does the gravitational force get bigger or smaller? And the answer is bigger, because if you reduce the radius, if the radius goes down, then the gravitational force must go up. One over 9 over 64, which can be simplified to it's just 1 times the reciprocal. So that's the factor, 64 over 9. The new gravitational field strength is going to be 64 over 9 times the initial gravitational force. Sorry, I said field strength and force. So we just multiply that by the original. And that gives us 64 times 10.5 divided by 9 equals 75. There's the answer for that one. The answer is 75 newtons, the force between the two objects. Next one, how far above the Earth's surface are you if you experience a gravitational field strength of 8.9 newtons per kilogram? Here's the Earth, here's you standing on the surface of the Earth. You are experiencing a gravitational field strength of 9.81 newtons per kilogram. And you are what distance from the center of the Earth? The radius of the Earth, which, just for your own knowledge, is this. You do not need this piece of information. It's on your formula sheet anyway, but you do not need this to solve the question. How far? Oh, yes, actually, you do need this one to solve the question. Because we want to know how far above the surface of the Earth. So now we are going to go up into space. And here we are up in space, and now we're up in space, and we forgot to put on our astronaut suits, so we're dead. So we're just kind of floating around there, and we're experiencing a gravitational force of 8.9. So yeah, you say, oh, it's not that much less. How far away from the Earth's surface am I now? All right. So which formula we can use for this one? We're talking about gravitational field strength. G, little g equals big G times m over r squared. And what are we solving for in this question? How far above the Earth's surface? So we're solving for the radius. So we'll manipulate this formula for the radius. The radius equals, just switch these two, the old switcheroony. R squared equals big G m over little g, and therefore R equals the square root of big G times m over little g. Plug the numbers in. 6.67 times 10 to the negative 11. You need the mass. The mass of what? Always the mass of the Earth, the mass of the object that you are referring to. That's 5.97 times 10 to the 24 kilograms divided by a little g. Now, what's your little g now? It's going to be the 8.9, because that's the gravitational field strength that you're experiencing. So stick all that in your calculator. I'm just going to move the answer over here again so I'm close to the mic and you can hear. The answer turns out to be, what does it turn out to be? Turns out to be 6.688905.79 meters. I'm just going to verify that. 6.67 times 10 to the negative 11 times 5.97 E24 divided by 8.9 equals, and then take the square roots of the answer. And yes, that's the answer. Okay, so, but then you got to ask yourself, what number is this? It's a big number. 1, 2, 3, 4, 5, 6, 6.69 times 10 to the 6 meters. Is that the answer to the question? No, because that is the answer. That is, let's go back up here. That is this distance from you out here floating around dead in space to, oops, the center of the Earth. And the question is not asking how far are you from the center of the Earth. It's asking how far above the Earth's surface are you. So you have to do one additional step in this. You have to take that distance, the total distance you are, is you. Here's this distance here, 6.69 times 10 to the 6th. And here's the radius of the Earth, which we just said is right here. That's the radius of the Earth. And you're going to have to subtract those values. So this total distance minus the radius of the Earth will give you what you want, the distance above the Earth's surface. So we're just going to subtract 6.37 times 10 to the 6 meters minus 6.37 E6 on your calculator, and you get 31890, we'll just round it off to the nearest meter, 6 meters, which is how many? That's 318,609 meters, which if we round it off to kilometers, it's going to be 319 kilometers. You are 319 kilometers above the Earth's surface. Onward and upward. The next one says the radius. Which number is this? This is number 5. Oh my gosh, we're at 50 minutes already. Okay, I'm going to stop And we'll do the last three on a separate video just so that the videos aren't excessively long.